Hey everybody. Okay, so this is a Plan B video. I was supposed to do this all via screen capture, but I'll explain as we go why that didn't work. So instead, you get me and the big screen. So anyway, this is a follow-up to what we did in class last week, which involved rolling funny dice and trying to figure out what the average roll was. So these are the blue dice from the set. Now I know a bunch of you had red or green or yellow or orange, but the blue ones, I just made the spreadsheet about the blue ones, realized the same thing would happen with any of them, not just the blue ones. Now the dice, if you recall, represent the population that we're studying. Theoretically speaking, what I did right here, you wouldn't be able to do in most populations, which is see every element. We can now look at all 36 possibilities if you throw this pair of dice. 1 and 5, 1 and 5, 1 and 3, 1 and 6, 1 and 3, 1 and 1. 2 and 5, 2 and, well, you get the point. We can actually line up all 36 of them. In reality, the population is much, much higher. As I'm talking, I'm seeing a guy down there who's thatching the grass. Why do we thatch grass? We thatch grass because ostensibly someone has studied lawns or lawn science or landscape science and realized that if you actually dig up all that dead matter that accumulates over the winter and then rake it off, it gives the grass a better chance at growing the following year or the following season. How do they know that? Well, I'm assuming it's because they did a sample where they did it and a sample where they didn't do it, and the sample where they did it performed better than the sample that they didn't do it. Now, I'm supposing all of this only because my ADD allowed me to hear the thatcher down there. Long story short, you couldn't do it to all possible lawns or all possible blades of grass, like you can see them all here. So what I want to focus on today in this next series of hopefully short videos, we'll try to go off on as few tangents as possible, hopefully short videos, is to see how you replicate the problem with not being able, or not replicate, how you fix the problem of not being able to measure the entire population. So here's the deal. This population has an average of 8.166666666. That's the average of this population. You, as a statistician, will never know that because that's a parameter. That's mu, a parameter value, okay? That you'll never know. So what do you do? What we did in class last time was we drew samples. We drew samples. Oh, that's actually a misprint. There are 1,000 samples in this spreadsheet right here. And if you remember, every time you rolled the dice 4 times, you would keep track of the sums you got. So this in sample 16, they got a 2, a 5, a 6, and a 7. In sample 17, they got a 6, 11, 11, and a 9. And then these are the actual averages of each of those samples of size 4 that are to the left. And that's what we did in class on your little in-class quizzes, which I returned to you yesterday. And the point of that was that to collate those results together and see what happened. And what happened with you all is kind of what's happening up here on the screen. What's cool about the screen is we can sit here and press F9 and get 1,000 new samples. Now I'm going to try something here. I should have tried this before I started recording. I wonder if I can get this thing to keep replicating while I walk over towards you. Hang on one second. Give me a sec. I apologize. This doesn't really count as a tangent. Oh, never mind. It's not going to work anyway. It's not going to work because the graph isn't catching up. That's okay. Okay. So I just stopped it at one point, although you might have noticed all the graphs kind of look similar. They got that bell shape. Exactly. Now, I want to make sure you know what you're looking at right here. I'm going to pick this sample because it's right in front of my face. This sample has an average of 8.75. That sample value, 8.75, is 1/1000th of this bell curve because there are 1,000 samples in this bell curve. So when I look at these axes over here, I notice the tallest axis. Well, let's go with this one because the math is easy. The height of this is 0.14. That is 14 out of 100. That is 140 out of 1,000. That means that 140 of these numbers are in that bar right there. Now that bar right there just so happens to be the bar that contains the population average mu. But you got to remember, you're not going to know this when you're doing your statistical study. All you're going to get is your sample value. You're going to get 8.75, or 9, or 7.25, or 6.25, or maybe you get 12, It's unlikely, but it still happened over here. You see how it happened over here? There was a little bar out there between 11.5 and 12. Maybe you end up down here at 3 to 3.5. It's unlikely, but possible. What's more likely, as I believe Devin pointed out, or maybe a few of you pointed out, is that you land closer to the average. And every time you replicate the studies, you land closer to the average. And this was the whole point of what we talked about in class yesterday, which was on average, the average we get lands at mu. The problem is this. This is what actually happens when you do one study. See, now there's only one sample. Here's what they got: 2, 12, 6, 7, with an average of 6.75. The actual population average we're looking for is over here at mu, but we landed here. Well, that's not really close. That's like 2 units away. Now I'm doing close in quotes because close is meaningless right now. Close, far, these are all relative terms and very, very wishy-washy. Therefore, we have to define them better, which is the point of the next few videos in this sequence. But right now, that's not very close. If I do another sample, I got just about as far away on the other side. Here's another sample. Okay, this one's still lower, but it's a little closer than the first one. Okay, this is actually kind of fun. They're alternating back and forth. Okay, that looks pretty darn good. As a matter of fact, whoops, this bar is technically, well, not that this really matters. This bar is technically in the wrong place. I must have moved the graph. That bar actually would have hit the average much, much more closer than it should have. That one's not as good, and you see what happens? Every time you do a sample, you usually don't land right exactly on the average that you're looking for. You land on average closer to it than you land further away. Watch that again. I'm going to run a bunch of samples now. There's a bunch of samples. Notice how most of them are landing in here and fewer of them are landing further away. That's because of the bell curve. The bell curve tails off, but you definitely are getting some that are landing well to one side. Let's see if I can get one here. And again, well to one side is also, that's pretty far off to one side. Well to one side is relative to, what do you mean when you say far away? So the problem is that, yes, on average, we land close to what we're looking for, but we only represent 1 in 1,000 of all the samples. And that number is much, 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 much smaller in general. If samples are replicated 10,000 times or 20,000 times, we're only one of those. So the question is, can we still do anything useful with just this? Can we do anything useful with just this value? Because remember, here's what technically you actually know about this study. That's what you actually know. You know that you ran a study and you got a sample average of, in this case, 7.5. Now remember, what I just deleted is an unknown quantity. You have no idea what that quantity is, that parameter. It's a parameter, it's a population measure. So all you know is that your sample average is 7.5. So what do? Do you say that, well, I learned this thing in Sean's stat class that said, on average, my sample average is part of a bell curve, and that bell curve is centered on average. Now, I think people would be happy with you if you said that, because at least they would understand you understood the central limit theorem. But the problem is that that 7.5 needs to be interpreted as an estimate for the population average. So in other words, how do you turn the estimate you got into something that speaks to the population average? And that's where the next part, the next series of videos is going to get from. So hang tight, and we'll lead into the next video here.